atlas.
Yes, thanks for introduction. Today I'm going to talk about some of recent work on construction of 3D atlas, where we translated this old book of Vogt school about this myeloarchitectonic map to the 3D cortical surface in the human brain. They really try to bring this old legacy information to the current neuroimaging field. Okay. Yes. So I think historically, how we can parcellate the human brain is really long-standing question in neuroscience. And then even before this modern neuroimaging era, many scholars and schools had already attempt to map cortical architectures, mainly based on the microscopic cellular properties, so-called cytoarchitectures. And here I prepare a couple of examples. And first one is Brodmann map, as you all know. And this is like Brodmann almost for the first time provide a subdivision of human neocortex, showing each brain area has different size, different shape, and different composition of neuronal cells. And after this, after a few decades, von Economo and Koskinas, as well as some other researchers, such as Russian schools, update this map, providing higher resolution and more detailed information about, as you see in the table, layer thickness, layer-specific thickness, or cell density or size information. However, at the moment it was created, it was written in German language, but luckily recently it has been translated in English book by this Dr. Trial-Hu, as you see this book. So now we have really good opportunity to correlate this or microscopic information to the macroscopic MRI-derived features. More importantly, recent work done by Dr. Martin van den Heuvel group made this information even more accessible to the community, because they literally took all this cytoarchitecture boundary information from the book of this von Economo and Koskinas, and then manually segment on the individual cortical surface, that is driver free surface, and then feed this manual label into the free surface parcellation function to be able to automatically segment this von Economo and Koskinas region. So you can imagine if you have new subject, you just perform free surface and apply a couple of additional command line, then you could directly have this von Economo and Koskinas parcellation. So this is really useful information, because if you have a new MRI-derived features, you can directly correlate those cytoarchitecture information, such as cell density or size or layer-specific thickness. However, you also know that cytoarchitecture is just one part to describe brain structures, and some other really important aspect that we shouldn't ignore is underlying myelinated fiber configuration, so-called myeloarchitectures. Unfortunately, this much autonomous way to extract the information has not been prepared for myeloarchitectures, so that we really need to bring in this old legacy information to the neuroimaging field. It is not surprising, though, those old school and scholars had hard work on already this myeloarchitectonic information. And then interestingly, most of the study actually come from the one research family called Vogt School, Oscar and Cecil Vogt, who start their research program very young age, but they devote their whole life for these myeloarchitectonic studies. And then as you see, from early 90 to 1970, they generate all these really important study on myeloarchitectonic maps. And then continuing this study, Dr. Rudolf Neuvenois here, he also himself is really great neuroanatomist, who is still alive, by the way. And he revisited all these studies and then performing extensive meta-analysis and create these recent 3 studies where he aggregate all these cortical boundary information from these studies and project to the modern standard brain template, which is called 27 individual brain. And then as you see, he created this myeloarchitectonic atlas, which consists of 180 myeloarchitectonic areas, and then also multiple subdivision of lobe areas. Another big contribution of Dr. Neuvenois is he also extract some other information, which is degree of density myelin fibers, and that the original information is actually come from the Dr. Adolf Hofs, who is another colleague of Vogt School. And then Adolf actually performed a photometric analysis on his multiple specimens and then manually draw this degree of myelination density on each brain areas. And then what Nouvenoi did was just taking over these figures and then digitizing, and then literally quantifying the level of gray level index from these figures to represent these myelin density maps. And then finally, he provides this table. As you see, across the cortical multiple cortical areas, he report this mean gray level index, as well as minimum and maximum gray level index, which you can flexibly deal with. So that, as I introduced just before, he also had this myeloarchitectonic atlas, so that he was able to map this gray level index on the cortical surface. So this is yet another really important resource. However, it literally remains as a 2D representation in the paper, so that there are all important information, but if you want to use this information, there's no way to do this, so that it's not really readily applicable to the 3D cortical manifold. So that what in this work, what we really contribute on top of this big work done by all the researcher was performing free surfer on Collins 27 brain to obtain cortical surface, and then comparing this anatomical correspondence between 3D surface and then 2D Nouvenoi atlas, and then we manually also translate this boundary information on the free surfer cortical surface with the ultimate goal to map this gray level index on the 3D cortical surface. There were, multiple issues that we have to deal with. The first one is because this old atlas is always done across the convexity hull of the cortical surface, so they never really open this buried surface, so that whenever the boundary cross this surface region, we just had to guess the position of this boundary. So what we did was basically just take the deepest point of the surface if it happens, and then just draw evenly splitting this brain two brain areas, as you see in these two figures. Another issue was is also related to the fundamental limitation of manual work. Some other parcel areas, as you see in this red highlighted area, they actually appear multiple times in different view. The first upper panel is actually medial view, and the bottom panel is inferior view. And then as you see, their morphology of this shape is quite different, so that we also had to select one of the views in order to minimize the conflict surrounding the areas. We also had another issue down here, hidden surface areas. This is also related to this first issue, buried surface. It's because the brain has this perisylvian fissure, so that unless you open this perisylvian fissure, you cannot really see this hidden anatomical area. So we had to isolate this surface, literally taking out all the brain structures and then manually segment there, and then again merge back to the whole brain surface. So finally, we make this myeloarchitectonic 3D atlas. We just coined along our name, MNI NOEL 3D atlas, and then as you see across the multiple views, so that we are really working on validation, how accurately we drew these boundaries. But as you see now, those area numbered, the correspondence between these 2D Nouvenoi atlas and then our 3D atlas are not so bad across the lateral and superior, and also medial, inferior, and then hidden surfaces. Some other validation analysis we are doing now is, the first one is, as you see in left side, using rather the in vivo surrogate marker for myelination, which is T1 weighted and T2 weighted images, so to calculate this degree of myelination. So we took the 20 healthy adults in Human Connectome project, and then just directly correlated between this mean gray level index and T1, T2 ratio. And as you see, it shows strong, robust negative correlation. Another little validation analysis we are doing also is, as I introduced in a couple of first slides, because Dr. Van Heuvel group provide this bone economer co-skewness atlas, so that now we also have this cell density and cell size, layer specific thickness information. So we actually just correlated between cyto and myeloarchitectural features. And then among those features, only cell size shows this strong or robust negative correlation, meaning that the highly myelinated areas, such as sensory motor areas, has a larger cell size, which is also previously well known. So this is my conclusion, and our MNI NOEL 3D Myeloarchitectonic Atlas was built based on the extensive meta-analysis done by Dr. Nubnua, and the association with MRI-derived myelin markers supports this biological validity, and it can be directly used for in vivo studies in healthy and diseased brain. And obviously, the whole point of this project is once we finish this all validation work, or we're going to release it to the public so that people can use both cyto architecture information from Martin van den Heuvel groups and then myeloarchitectural information from this work, so that it can really correlate between microscopic and macroscopic features. With all that, I'd like to thank to my lab members and funding source, and thanks for your time.